Hello, and welcome to the Solutions in Molarity video. So what is a solution? Well, solutions are homogeneous mixtures, and this is a term that we described earlier in the quarter. This is when we have a mixture where the components actually dissolve into each other, and they're uniformly mixed is another way to think about that. And in solutions, we'll often refer to what's known as a solvent, and a solvent's the material present in greatest amount. So whatever the majority of our solution is composed of, it's going to be the solvent. And oftentimes this is going to be water, but really any material can be a solvent. But again, generally we'll be talking about water when we talk about solvents in this class. And we can also have solute or solutes. These are the materials present in lesser amount. So in this case it'd be table salt, but we could have all different examples. So like in coffee, for instance, we'd have caffeine dissolved in there and sugar and other things as well. So our good friend Dwight right here is letting us know that our solvent doesn't have to be a liquid. Our solvent and our solute and our solution itself, for that matter, can be any state. So if we take a look at our next slide here, we can have gaseous solutions. So air is a great example of this. So in air we have oxygen as the solute and nitrogen as the solvent. And of course we have other solutes mixed in air too. Air has water vapor and CO2 and methane and argon and all kinds of other stuff. So kind of a complex mixture, but our solvent and our solution itself are actually gases in this case. In liquid solutions, we can have solids dissolved into our solution, so solid solutes, or we can have liquid solutes. Another example of this would be like hydrogen peroxide. That's actually a liquid dissolved into water. And we can also have gaseous solutes dissolved into our liquid, in this case water, like household ammonia or carbonated water are examples of these. And we can even have solid solutions, like they give the example here of brass and steel. So these are metal alloys right here. In order to get these to mix, we actually have to melt them down together, but these are still solutions. So brass is when we dissolve zinc into copper, and steel is where we dissolve carbon into steel. And so again, the key takeaway here is that our solvent, our solute, and our solution can be any state of matter. So please pause the video and complete question number 1. All right, welcome back. Let's talk a bit more about solutions. So water is our most common solvent we'll be talking about, and water is really good at dissolving things that are polar or things that are ionic. So right here are water molecules. These are polar molecules. We talk about that in the end of the sort of molecules chapter. And what happens here is these water molecules are attracted to the cations and to the anions. So right here are sodium ions, which are positively charged, are attracted to the lone pairs on the oxygen atoms of the water. And the chloride ion, on the other hand, is attracted to the hydrogen end of the water molecule. So water, because it's polar, can be attracted to either cations or anions. It just sort of does a 180, just flips around in order to attract both those. And so the key things to note here is that water is polar, and therefore it's able to interact with ionic compounds. And when they dissolve, they actually separate into ions. So there's a term for this. It's called dissociation. And anything that forms ions is going to be known as electrolytes. So if you don't know what electrolytes are, they are things that form ions when dissolved in water. So what are our different types of electrolytes? Well, we have strong electrolytes. And strong electrolytes completely separate into ions. And strong electrolytes are going to include things like ionic compounds, strong acids, and strong bases. And if you don't know about acids and bases yet, that's fine. We're going to cover that in a future chapter, so don't sweat that for now. Just do remember, though, ionic compounds, strong acids, strong bases are strong electrolytes. Now we also have weak electrolytes. And so weak electrolytes, they produce some ions, but not very many in solution. And weak electrolytes are going to be weak acids and weak bases. And then finally we have non-electrolytes, and these are things that do not produce ions when they dissolve into water. So good examples of these are going to be sugars, like anything with the ose suffix, like dextrose and maltose and sucrose and glucose and fructose and lactose and all of those. And also alcohol, so things like ethanol or methanol or isopropanol, so they have a similar suffix to each other as well. So those are non-electrolytes. They don't produce any ions. There's a very simple way to test if something's an electrolyte. If you dissolve it in water, the water will only conduct electricity if there's ions present. So with a strong electrolyte, what we see is our water actually become highly conductive when a strong electrolyte is present. Now, if we have a weak electrolyte, well, we're going to see a small amount of electricity being conducted. So that's why we have the dim bulb here versus we had the very bright bulb in the previous slide or previous picture. And then over here we have a non-electrolyte, and we can see that there is no light coming from this light bulb. So this one is a non-electrolyte, and the problem is because we have no ions, our water can't conduct electricity. So one of the things I want you to be able to do from this chapter is predict what ions are going to form when you dissolve strong electrolytes in water. So right here we have calcium chloride being dissolved into water. So what is it going to form? Well, what's going to happen is our calciums and our chlorides are going to dissociate from each other, and the correct answer here is C. We're going to end up with our calcium 2 plus ions as well as 2 chloride ions. And for this one right here, we have potassium phosphate, and so now we're going to end up with 3 potassiums and a phosphate, so A is actually the correct answer here. So notice if we encounter a polyatomic ion from our list, that polyatomic ion doesn't break down further when we dissolve. So right here, this Cl2, that's not a polyatomic ion that we're familiar with, so that's going to dissociate into the individual ions. But if you encounter one of the polyatomic ions that are from the list, then assume that's going to stay together as one big unit. Let's see how we did. Oops, too far. Ah, fantastic. We're brilliant. All right, so please pause the video and complete question number 2. Welcome back, everyone. Let's talk about our next topic, and our next topic is going to be concentration. So, because solutions are mixtures, the amount of each component can vary. So if we think about the example of like salt water, for instance, we can have a lot of salt in that water or just a little bit of salt in that water. And we're going to refer to the amount of solute in our solution as concentration. And concentrations, again, usually some sort of ratio where we have our amount of solute, and our units are going to vary, but amount of solute over our amount of solution. Again, the units will vary. We're going to talk about 3 different ways of doing this. So we're going to focus on mass percent, volume percent, and molarity. So let's talk about mass percent. So mass percent is pretty simple. It's the mass of our solute over the mass of our solution. And our mass of our solution is simply going to be the mass of solute plus the mass of solvent. And then we take this quantity and we multiply it by 100. So if we prepare a solution that contains 8 grams of KCl in 42 grams of water, so that's going to be, here's our 8 grams of solute up on top, and 50 grams of solution. So where did the 50 come from? It's going to be our mass of solute plus our mass of solvent. We crunch our numbers, and our percent concentration here is 16. So again, mass of solute over mass of solution times 100. Pretty simple to calculate these. Moving on from there, volume percent is very similar, except it's going to be volume, typically in milliliters, of solute over volume of solution. So a bottle contains 59 milliliters of lemon extract and 49 milliliters of alcohol. What is the volume percent of the alcohol in this extract solution? So we're going to take our volume of solute, in this case alcohol, and we are going to divide that by our volume of solution, and then times 100, and we're going to end up with, when we crunch our numbers here, 83% by volume alcohol. So very similar to before, but now we're doing milliliters over milliliters instead of grams over grams. And so another unit of concentration I want you to be familiar with is molarity. We're going to be talking about molarity a lot. And you might have noticed that when you looked at some of the bottles in lab, you might have seen this uppercase M on them. So the uppercase M is our symbol for molarity. And uppercase M, or our molarity, is going to represent how many moles of solute are in every liter of solution. So again, it's a ratio, moles of solute over liters of solution. So we're asked here, what is the molarity of a 0.350 liter solution that contains 46 grams of KCl? Well, we need to find moles, because we need to find moles and liters here. So the liters are given, that's simple enough. We're going to find our moles of KCl. We're going to do that from our periodic table. We'd add together the atomic mass of the potassium and the chlorides. And so then we're going to end up with some conversion factors. We're going to pick the one on the left here so we can cancel out our grams. And so we're going to bring down our grams right there. Convert that to moles using our molar mass, and we have 0.62 moles. And we're not done yet. This is moles, not molarity. So I want to point out people often and understandably mix up moles and molarity. Moles and molarity are different things. Moles are essentially a unit of how many particles we have. Molarity is moles over liter, or particles over liter, essentially, is another way to think about that. So again, we're not done. We found moles, but not molarity. So molarity is going to be our moles divided by our liters. So here's our moles we just calculated. We're going to divide that by our liters of solution, and our molarity here is 1.8 uppercase M KCl, so molarity. And people might often also write that as something like this. We'll do our MOL to abbreviate moles, and then slash liters is another way of sort of writing the same thing. But these are both popular, both commonly used, the uppercase M or the moles over liters. So let's do another problem here. How many liters of a 2 molar sodium chloride solution are needed to provide 67.3 grams of sodium chloride? So to solve this bad boy right here, we're going to take our amount of sodium chloride and we're going to bring it down, and we're going to use our molar mass on it. So our molar mass we get again from the periodic table, and we're going to use that to cancel out grams and end up with moles. And then we can use our molarity. So now we're going to use our molarity here. That's where this quantity comes from. And the moles are going to go on the bottom here, so we cancel out the moles over there. And that's going to give us a volume of 0.575 liters of sodium chloride solution. All right, so I'd like you to now pause the video and please complete questions 3 and 4. And we're going to continue in part 2. So again, we'll pick up in part 2 of this video.